I was on this table on Tuesday. So these are some real data. You can find the data on this particular website of the US National Institute of Standards and Technology. They maintain and constantly update energy levels obtained by spectroscopy for all the elements in the periodic table to high accuracy. So the number here are actually part of the accuracy. There are 4 other decimal points here. So I would like to show you the website. So here you can Google NIST database, and then you get into a place called lines and levels of all the atoms. I just typed in hydrogen, and this is what I found. So you see the table all right on your screen, right? So here 1s is set arbitrarily to 0, the ground state, and then it started out with the 2s. You see, I only copy the first 4 digits out, and there are 6 others. So spectroscopy is a not too expensive way, but highly accurate method to determine the energy levels by measuring transitions, spectral lines. And then you see there are 2 numbers for 2p. Again, I copy the first 4 numbers, and there are several remaining. And then all the way down, you have all these levels. I would like to show you that there are numbers not so accurate though, even for n equals 40. So it's very difficult experimentally to selectively excite hydrogen atom to the n equals 40 level, but not ionize the electron. And then there is a limit. This limit means just ionize the electron, okay? So if you want to look into other elements, very accurate data, you can find it here. So let us go back to our own class notes. So these are a few ones that we selected out. First of all, look at the ground state to the just ionized situation. So this is the ionization energy, 13.6. That's what we know from Schrödinger equation solutions. So here you see the number is this many wave numbers. Last time I introduced that experimentalists talk about centimeter inverse, which is how many wavelengths are there in 1 centimeter length. That actually also tells us about the energy. If you have some conversion with h, the Planck constant, and the speed of light. Doing the calculation, it amounts to 13.59843 eV. So that actually came quite close to what you solved from the Schrödinger equation, especially when you use the reduced mass instead of the bare electron mass. I look at your class notes by Professor Liu. He used the reduced mass for this hydrogen atom problem. That is the correct approach, because if you don't, basically, even in classical mechanics, there is some problem. You have a proton, you have an electron. The center of mass is closer to the proton, and then as it orbits, if you don't use the reduced mass, the center of mass will be making a small circle, but there's no external force. The internal force is Coulombic. So even in classical mechanics context, we should replace the M in the Schrödinger equation by the reduced mass. I know that you have done that. You know this piece of physics. Now let's look closer to the 1s and the 2s2p levels. So intentionally, I copy the data out. So this is 1s set to 0. We see that 2s has a number, 2p even worse. There are two numbers. In Schrödinger's solution, all this should be minus 13.6 divided by 4. Okay, so n equals to, the energy is minus 13.6 divided by 4 GeV. Okay, that is the number for this 82259 or so. But accurate measurements reveal that there are actually three, but very nearby numbers. So first of all, Schrödinger equation with the Coulomb term works very well. Almost there, 99.something%. However, as physicists, we care a lot about tiny discrepancies. So this is in the, less than 1 out of 80,000. Okay, 1 part out of 80,000. That is that tiny accuracy. Graphically, it is something like this. Instead of these three numbers come out to be just one number as predicted by the Schrödinger equation. So I would like to point out that there are something more for us to understand, even within the hydrogen atom. So what are the effects that we need to consider? So hydrogen atom, the Hamiltonian, plus something. What could that something be? It turns out to be a lot of things. Now, first of all, in week number 2, last week, a sample question number 1 showed that there is some relativistic effect, correction, to the kinetic energy term. This week, the TA worked out the first order perturbation correction for that term for any states. Not an easy calculation, okay? But that can be done analytically, nice. In addition to that, when you talk about relativistic effect, there's one important effect that we cannot ignore, which is spin effect. After all, spin is an relativistic effect for the reason that spin comes out naturally in the direct relativistic quantum mechanical equation, so-called Dirac equation for the electron. So if we care about the relativistic correction, then we should also consider effects due to spin. We will discuss in more detail one particularly important effect called the spin-orbit interaction a few sections later. So to summarize this part, first of all, even hydrogen atom, though simple, it's a very important question to understand. For those highly motivated students, I would like to encourage you to write for yourself a term paper on the physics of the hydrogen atom. If you can follow everything in hydrogen atom, at least you know quantum electrodynamics. That is not an easy topic to write about, but you could try to the extent that is within the physics that you know up to this point. You don't need to go to the last correction called lamp shift. However, it is a very interesting and educational topic. Secondly, spectroscopy is a good and cheap experimental technique that continue to inform the development of new physics. And lastly, I would like to emphasize one more time that physics is an experimental science. Its development is often driven by accurate measurements. There's some discrepancy, and then ask the theorists why. They will come up with some explanation, and then new experiments come in, and there is an even smaller discrepancy. Why so? Okay. A remark here is that the hydrogen atom physics is now being done at CERN concerning anti-hydrogen, anti-proton, trap a positron. This is the only antimatter formed by artificially by human. Okay, and then how could they study this? What else can it be? Spectroscopy. This is some very recent experiment. So last page before we get into the business. So we will be doing the following. I hope that you realize this is the hydrogen atom Hamiltonian that you played with last term. You know the solutions. Now we need to add some small effect. So perfect for perturbation approach, variational calculation, etc. So what this could be, there are effects that are intrinsic to the atom, meaning you don't need to pay, you don't need to buy a magnet. External field, electric field, is not external, it's internal. You cannot avoid them, okay? There are examples here, relativistic correction, we already seen. Spin orbit interaction, we will discuss. There are also extrinsic effect, meaning you have money to buy a big magnet, then you can apply an electric field, okay? A magnetic field, sorry. And then you can use a current loop to apply a electric field that is going to give us some external effect that comes into this Hamiltonian as that extra piece. Later on in the course, we will send in EM waves to let the atom absorb, or the atom will emit. That has to do with time-dependent perturbation. This term will be time-dependent. We need another new tool before we can get into it. We will do it in a module called light-matter interaction later. Okay, so that set up the stage. So let me go on to the very first effect. Again, if you have questions, you may type it into the chat box, and then I will answer them. And then in the break and after the class, I will stay on to answer all your questions, all right? So the first thing we would like to do is a very famous effect called the Zeeman effect. Again, this simple effect has driven the development of quantum physics. So this is the first encounter. After 60 pages of notes, we will have a second encounter of the Zeeman effect. So in this part, I will do the simplest version of the Zeeman effect. First of all, let me define broadly what is the Zeeman effect. So in the Schrödinger solution of the hydrogen atom, you have n equals 1, you have n equals 1 down here, n equals 2 up there. There is a 10 eV difference. In the 19th century, this particular transition will give us one line in the Lyman series. I think it's in the ultraviolet, just one line, okay? Then what is Zeeman effect? The Zeeman effect corresponds to the following broad phenomena. When you apply an external magnetic field, we are talking about B fields. When we apply external magnetic field to an atom, and then we measure the spectral lines again. When we see some lines, originally one line split into several. That several may be 3, but even worse, sometimes maybe 6, maybe 10. Under an applied magnetic field, all this splitting of a spectral line into several are collectively called the Zeeman effect. Okay, so at this point, I defined the phenomena. The next thing is, why so? Can we explain at least a little bit of this Zeeman effect? So in this first encounter, we will not include any effect of the electron's spin. In an atom, you have electrons running around, right? So hydrogen, you have 1. And electron, you know, last course, it has a spin, angular momentum. For this part, don't worry about it. We don't consider the effect of spin yet, all right? So we will ignore spin. Therefore, what is left is the orbital angular momentum of the electron in the hydrogen atom. So all the effects here will be due to orbital angular momentum. Therefore, the first thing is to consider what is that something? What is that extra perturbation term? The mathematical form of which to be included into the Hamiltonian. So that is the first question. Okay, I will develop the answer for you. For the purpose of this section and for the purpose of doing quantum mechanics in real context. When you do quantum mechanics, you need to write down the Hamiltonian. One easy way is think classical first. What do I mean by that? Go to your classical physics knowledge and think about what is the effect if you have a magnetic dipole moment due to orbital motion in the presence of an external B field. You look up your Griffiths about chapter 5, chapter 6 on magnetic effect. So here I start the discussion based on that. So we have an orbital angular momentum due to electron. Because electron has charge minus e, there is an associated or an magnetic dipole moment that goes with the orbital angular momentum. This is an equation that you have seen last term. Have you? I saw it in the notes, okay? So, in your notes. So we will take this as the starting point. The minus sign here is a convention because we assigned the minus e to electron once upon a time for historical reason, okay? And therefore, when an electron moves this way, the current loop move another way, and thereby a small loop of current will come with a magnetic dipole moment. That is the classical physics. All right. So now let's write it into a more common form. I multiply a H bar, I divided a H bar, nothing, right? I've done nothing. But this combination is a very important piece of knowledge for all physics students. First of all, it's a lovely combination of constants. Charge, Planck constant, well, divided by 2 pi, H bar, and then electron mass. If you plug numbers in and then get the number out, it is about 10 to the minus 5 eV per Tesla. Tesla is the unit of magnetic induction, magnetic field, the B field, all right? So it is a constant, first of all. It's so important that it is given a name. It is called the Bohr magneton, okay? I call your attention to this spelling. It's not magnetron, it is a magneton. There's no R here because generation of students spelled it wrong. I hope my students won't make that mistake. Okay, so now after doing that, it is minus a constant, then the orbital angular momentum divided by h bar. You know, in quantum mechanics, h bar is the natural unit of angular momentum. Thereby, this combination has no unit that will be useful. The last step, I insert a 1 here. I inserted something called the G factor, but for this context, it's a boring 1. But in order to shape it into a more standard form, I include the G factor of 1 here. Okay, so let me summarize. Magnetic dipole moment that goes with the electron's orbital angular momentum is related by mu. There's a minus sign due to the charge. There's a Bohr magneton setting the strength, how big this magnetic dipole moment will be, and then GL divided by h bar, okay? Then I look into your Griffin's textbook, electrodynamics. In the presence of an external B field, the interaction energy is minus mu dot B, okay? So this is a magnetic interaction energy that works as a potential energy term that will go into the Hamiltonian, and thereby you have a perturbation term. So it is just a remark here. If my atom is isolated, alone, nothing else surrounding it, okay? It has no sense about what is X, Y, Z direction. Well, in your solution, you have all this X, Y, Z functions or alpha theta phi functions with a Z direction chosen, right? But for an isolated atom, it is just our choice in doing the mathematics. However, once you have a magnetic field applied, there is one special direction, which is the direction of the magnetic field. So once you have an applied field, there is a special direction in the problem. Then you can call it whatever you want. A convenient choice is to call that direction Z. And then you can use the solution with that particular Z direction, okay? But even you choose that as Z is still general because there's a direction, you call it Z, so what, right? So the second step in getting a Hamiltonian is to go quantum. Okay, so 2 pages before, classical thinking, we get this form. Go quantum means promote everything to be an operator. All right, so this magnetic dipole moment becomes an operator because it carries an orbital angular momentum operator in it. So now this dot product, when I pick the B field in the Z direction, the dot product will pick up the Z direction of the magnetic dipole moment. Okay, so this is why we have this as the perturbation term. Writing it out, we have a mu BB, that is the Bohr magneton, a constant, B field, 1 Tesla, 2 Tesla, that's about it, okay? Only if you go to National Laboratory of High Magnetic Field, you can get something like 10 Tesla, or at best, maybe 100 Tesla, but only as a short pulse. That cannot be maintained for, I think, over a few seconds. Okay, so in the lab here, we can buy a magnet of about 8 Tesla. So only order 1, that's what I want to say. Okay, this B field, 1 to 10 Tesla. And then we have picked up apart the Z component of the orbital angular momentum. All right, so this is the perturbation term. All right, this goes into the hydrogen atom plus this thing, and that is the Zeeman effect without spin. Okay, so before we move on solving this with any of our tools, some common sense kicks in. You ought to know this Bohr magneton is of the order of this. Okay, so take it less seriously. Take the prefactor as 10. It is 10 to the minus 4 GeV per Tesla. Okay. Given that you have money to buy a 10 Tesla magnetic field, okay, people won't like it to be nearby. We have one, I think, maybe up to 8 Tesla in one lab in the department. So even if it is 10 Tesla, you multiply into it. So we are looking at correction term of the order of magnitude of 0.001 eV. That's about it. That should be compared with the transition. Say n equals 2 to n equals 1. That is a 10 eV transition. Okay, you get the point? Originally, it's 10 eV. If I add some effect into it, I know there may be some splitting here, but the splitting up there in n equals 2 are of the order of 0.001 eV. Okay, now a reasonable picture emerges, right? We have seen those numbers in the data. They are very nearby things in the n equals 2 group, very tiny correction. And now we started to get something like that, okay? Good sign. You should carry this number with you, all right? And then a byproduct is as follows. Now this is the Bohr magneton. You know there's something called the nuclear magnetic resonance, right? In nuclear magnetic resonance, this mass is no longer the electron mass, but you take it as a proton mass. Nucleus, there are many protons, and then proton mass is much bigger than electron mass, right? Maybe 10,000 times of that order. Is that right? Let me see. Electron is half MeV. And then proton mass is 1000 MeV. Okay, so maybe 2000 times bigger. Therefore, the Bohr magneton for a proton will be 10 to the minus 8 eV per Tesla. The effect will be even tinier. Get me? Okay, so the situation is summarized here. Last term, no external B field. You solved this happily. This term, we turn on a magnetic field. We found there is a perturbation term. We derived the form of the perturbation term H prime. It is this part. So we have a new problem. What you know, plus an extra term. So this is a classic situation to exercise whatever we know in our toolbox. Okay? So these are the things in our toolbox. What to do with this? Okay? You may wonder, let's do perturbation theory. Good for you. And then what else? Try first order perturbation. Good for you. Okay? And if you do that, a happy coincidence come up. You do first order perturbation, you got the exact result. You solved the problem exactly. So, advertisement, this problem this part, if this is the only term, this problem can be solved exactly. Now here, I just want to give you a short review on orbital angular momentum and some hydrogen atom physics. Okay? You should review the part in your class notes last term to get the 100% preparation. But here, just very basic thing. Because we hit at the orbital angular momentum Z component here, we better know a little bit about orbital angular momentum. So this is a definition, same trick, think classical. This is classical mechanics. After this, go quantum, raise them into operators. Okay, then you use Schrödinger's suggestion. X, Y, Z is just X, Y, Z. Px is the derivative of X multiplied by H bar over I. Okay, if you do that, you have this operator for the X, Y, Z directions. And the square, magnitude square, is this operator. You also have worked out the commutators between these four quantities. X, Y, Z components, and the magnitude square. These are the 6 commutation relations. In another part of this module, we will discuss what general results we could obtain by considering these 6 commutation relations of angular momentum in quantum mechanics. That will come later. For the moment, you have seen these 6 commutators by playing with this 4 explicit form. Okay? In quantum mechanics, if you have one quantity, a vector quantity with 3 components, and they obey these 6 relationships, they are generally called angular momentum in quantum mechanics, even though some of them don't look like angular momentum at all. This is the definition of angular momentum in quantum mechanics. Then you solve the hydrogen atom problem. Hydrogen atom has the lovely thing about spherically symmetrical potential energy function, because the Coulomb form only depends on the radial distance r and not theta phi. Thereby, you use spherical coordinates to do the problem for convenience. Then you have seen the square of the orbital angular momentum is this operator, and the Z1 is particularly simple because we choose the Z1 to be simple. We define the axis there and count the theta from that direction. Because of that, it is just a dd5, h bar over I, all right? The solution to this thing, you have also worked out. They are called spherical harmonics, YLM theta phi. Just to remind you, the eigenvalue of L square is this form. And the YLM theta phi are also simultaneous eigenstate to LZ with the eigenvalue mh bar. Summarizing, there are two indices in the spherical harmonics. L tells us how long the orbital angular momentum is. M tells us what is the Z projection, the Z component. Okay? And the radial part can be solved by using this Hamiltonian. Okay? So this is the Hamiltonian with R theta phi hidden here. This is the Hamiltonian written in spherical coordinates. Okay? We solved that. Well, you solved it last term. The answer is there is a radial part carrying N and L as the indices, and an angular part, spherical harmonics. Altogether, this is the energy eigenstate of the hydrogen atom. All right? There are three quantum numbers. They are simultaneous eigenfunctions of three operators. Hamiltonian, generally with energy depending on N and L. L square, provided by L, and LZ, given by ML, all right? For Coulomb, there's an accidental degeneracy. The energy only depends on N. This is not the most general dependence for spherically symmetrical potentials, but for hydrogen atom, it turns out to be so. Okay? So this is a very quick and brief revision on hydrogen atom physics. So for the discussion here, I pick up this line. I pick up this line, all right? So I move on. I copy these two lines here to emphasize that the atomic hydrogen energy eigenfunctions are also eigenfunction of LZ, okay? And more generally, if you have an atom that is not hydrogen, the atom part will give us an energy that depends on N and L. For example, 2s is 2, 0, okay? 2p is 2, 1, all right? So let's go back to the Zeeman problem, Zeeman effect. We work out the physical problem. It is the hydrogen atom or the atom part plus a Zeeman term. Now, you may think, let's do perturbation theory. It turns out that even perturbation theory is too high-tech for this problem. We can solve it exactly and more importantly, without any effort at all, with zero effort, basically. Because this atom part wave function is automatically an eigenfunction of this extra term LEZ. Therefore, we can solve this problem exactly. Okay? So the physics is that we have this Zeeman effect, and this is also an eigenstate of LEZ. Therefore, let's operate the full Hamiltonian onto the atomic energy eigenstate. So we have two terms, the atom term plus the Zeeman term. This will go into both terms. This is the old problem you solve. So generally the energy is this. Then pay attention to this particular bit. The perturbation is proportional to LEZ. And that wave function is an eigenstate of LEZ with eigenvalue MLH bar, all right? So therefore, automatically, it gives us this eigenvalue times the same eigenfunction. This combination are constants. Therefore, we solved the problem. Factorizing the wave function now, H psi equals a number psi. The new eigenvalues has been modified by the B field. Nonetheless, we solved the problem exactly. Okay, I pause here. Do you understand? Because we are done. We are done with the treatment of the Zeeman effect due to orbital motion only. The rest is to explain the consequence, the physical effect. Okay? Any question up to here? Hello, are you here? Any question 有冇問題? No? Okay, good. At least some respond. Okay, thank you. So let's move on. So we are done with the mathematics. Okay? In our toolbox, we use one thing, exact solution. Okay? The most important thing. And we are done. Okay? Now, I would like to discuss the consequence, the effect. What are we going to see in experiments? I think that is also an important part of physics, not only doing the math. Okay? So, immediately we see the new energy now depends on the third quantum number. Okay? Previously, even in general atoms, not hydrogen, the energy will only depend on two N and L, two numbers, all right? So 2P, you have three things, right? Px, Py, Pz. They are of the same energy. But now, with a B field, the additional thing depends on the third number. So ML equals 1, 0, minus 1, they will give three slightly different energies. Get me? Don't be too exaggerating. Remember, ball magneton is tiny. B field, not big. 2 Tesla, 8 Tesla. So what? Okay, so this thing is about 10 to the minus 4 eV. Okay, nonetheless, it depends on a third number. Okay, meaning the degeneracy behind ML is now removed. That is the key physics to keep in mind, not the math, okay? In the presence of a magnetic field, the originally degenerate state due to M, the quantum number M, the LEZ M, all right, is now removed. this degenerate state will become non-degenerate, slightly different. Get the physics? All right. So let me contrast the two cases. No field on the left, you know it last term. With field on the right, we get this extra bit depending on M. All right. Remove the degeneracy. All right. Important effect. The last time you said closed energy should also need. Right. But now there's a question here. The student said last time, I said, when energy are closed, we should use degenerate perturbation theory. Very good. So the question meant, so in this unperturbed problem, I have degenerate state. Why shouldn't I take that part out and do it exactly? All right. Now my answer. By solving it exactly, we have done that exactly. That part turns out to be diagonal by itself. The off-diagonal terms are automatically zero. So effectively, we have done degenerate perturbation theory, or another way to say it is we need not do degenerate perturbation theory. Is that okay? Because we solve it exactly. The Hamiltonian is automatically diagonal. Now, no more off-diagonal term. When you don't have off-diagonal term H prime Ji, you don't need to do perturbation theory. Is that okay? Hello? Okay, so good, very good, sharp eyes, wonderful, good. Okay, so now I will flash you the effect before I take a short break, all right? I don't want the flow to be interrupted. So here is a figure. This is a D state, for example, 3D. D, L equals 2. M, 5 values, 2, 1, 0, minus 1, minus 2. Without B field, they are degenerate. With B field, they become slightly split. Okay? How big the splitting is, look at this form. M is 2, M is 1. The difference is this constant. Ball magneton times how wealthy you are to buy a big magnet. Okay, mu BB. As I said, this is 10 to the minus 4 EV, about. So it is equally spaced, split out. The splitting is mu BB. All right. Now, similarly for P state, L equals 1, you have this. Okay. Now, after the break, we will discuss the transition. So you have some P state split, S state not splitting, simple picture. One line, no field. Get me? 3 very close nearby lines, you turn on the B field. One line becomes several. One line becomes several. That is Zeeman effect, explained by simple quantum mechanics. Okay, I hope that you are happy. And then we take a short break.